Hi all, and welcome to the Medical AI Lab reading group. Every Thursday, a lab member covers a recent paper in either core AI or medical AI, and these sessions are targeted to be broadly interesting to those interested in the cutting edge of AI and its applications to medicine. This week, we will have Julian Acosta kicking us off with a discussion of the paper, Advancing COVID-19 Diagnosis with Privacy-Preserving Collaboration in Artificial Intelligence. So without further ado, I'd like to welcome Julian to share this paper with us.
Thanks, Pranav. Hi, everyone. I'm going to share this paper now. As Pranav mentioned, Advancing COVID-19 Diagnosis with Privacy-Preserving Collaboration in Artificial Intelligence. This paper was published recently in the journal Nature Machine Intelligence. So as a little bit of background, reverse transcription PCR is the primary diagnostic modality to detect COVID-19 infection. But the problem with this modality is that the sensitivity is relatively low at 0.6, 0.7. So alternatives to improve the testing scalability and accuracy are needed. One of the options to improve detection is using imaging, and in particular chest CTs, because COVID-19 patients present certain radiological features that may distinguish these cases from other respiratory infections. However, using CT for diagnosis is not entirely accurate, and furthermore, it depends on the radiologist's knowledge and experience. So with that in mind, an automated AI method would be desired, but there are data challenges to accomplish this. First, the incompleteness of the data, because not all of the features that may be interesting to distinguish these patients are captured with the data that is already available. Also, isolation, meaning that these CTs are usually within hospital systems that cannot share the CTs easily with each other. And also heterogeneity, because the data that we have is also very heterogeneous in the sense that several different types of the scanners and protocols exist, and that may pose an additional challenge to accomplish the goal. Just to give a little bit of background and context to this, these are kind of the features that we talk about when we say that there are some features that may distinguish COVID-19 from other infections in the lungs. Just to show this, this is what they refer with. They talk about ground glass opacities, and this is what they refer with. Talk about crazy paving when there is these ground glass opacities, and also there is a little bit of interseptal thickening, and it looks like crazy paving. But these features alone are not very specific for COVID-19. So there is a lot of classifications to try to understand which is the typical appearance of COVID-19 in chest CTs. So usually when you have a combination of different features in chest CTs, you can say with a certain amount of confidence that this is a typical appearance of COVID-19. And usually what happens is you have peripheral bilateral, these ground glass opacities with or without consolidations and this crazy paving pattern. And as you can see, there are different kind of classifications that show go from a typical appearance to an indeterminate or typical appearance, or of course a negative chest CT. So coming back to the paper, what they propose in this paper is using federated learning in conjunction with homomorphic encryption to try to create a model that is accurate and generalizes well to the entire population. So the idea behind this is that there is one cloud server that basically stores the model and shares this model with each of the hospitals. Then the hospitals within their local systems perform certain number of iterations of training iterations, and then share this updated with the cloud server that aggregates this information from different hospitals and updates the model. So I'm going to go deeper into that in a minute. So first, a quick view of the methods. They constructed basically a data set from 2 countries, China and the UK. So for the China data set, they use data from 3 different hospitals. And the largest hospital that I included had 3 different campuses. So they had almost 6,000 chest CT images from the 3 branches. And in this case, there were similar acquisition protocols for these images. And all of these images were taken without contrast. For the COVID-19 patients, this come from January 7, 2020 onwards, and the control had an event horizon dating back to 2016. And they performed a train val and test split of 80 to 20%. Then the other 2 hospitals, they only had COVID-19 cases, and they only were used for the testing split. The UK data set was a little bit different. There were a lower number of CTs, and they came from 18 different partner hospitals. So the acquisition devices and the protocols varied widely from hospital to hospital. And there were, for example, 17 types of CT scanners. And importantly, most of the CTs were done with iodine contrast. So it's very different from the distribution from the CTs from China. And this is just the distribution of cases that were into the train val and testing split. So I'm going to just explain a little bit of the data processing that they did and the model architecture and the training setting that they did. They used an adaptive sampling method to select only 16 slices from all sequential images using random sampling positions. And they performed 1 sampling for the CT in training, but 5 different samples for testing. And the final decision that the model outputted was based on an average from the 5 samples. They standardized the slices, and they resized also the slices from 512 to 128 pixels along each axis. And they also set the lang window of images, the lang window for the CT images in this range of Hounsfield units. This is the architecture that they use. It's called a 3D DenseNet, so it's just basically a 3D version of the DenseNet that we know. They also use a 3D drop block instead of just regular drop out, because it can show that it's better for this kind of imaging processing. For the training, so the 3D DenseNet took pre-processed CT slice sequences and output a prediction score over the 4 possible outcomes that were the different pneumonia types. So the different outputs could be COVID-19 pneumonia, bacterial pneumonia, other viral pneumonia, and normal CT. They use for this a weighted cross entropy, and they assign the weights in this manner. So basically 0.2 for healthy, 0.2 for COVID-19, 0.2 for bacterial pneumonia, and 0.4 for other viral pneumonia. They use a 3D optimizer with a momentum of 0.9 and a batch size of 16. And they linearly increase their learning rate during the first 5 epochs from 0 to 0.01. And then they use cosine annealing to decrease the learning rate to 0 in the remaining 19 epochs. So they train the model for 100 epochs. So they use 5-fold cross-validation on the train val space first, and then they selected the best model and reported the test performance. And this is kind of the most important piece of the paper, which is the approach they took for privacy preservation. So in summary, they use a combination of federated learning and homomorphic encryption. For federated learning, they use the FedApp algorithm that was also by Google several years ago to aggregate the model parameters from all clients to combine the weights with respect to the client's dataset sizes and number of the local training epochs. And I'm going to explain this a little bit more in a bit. And then they use also learning with error-based encryption to secure the transmissions. So homomorphic encryption is just a variant of the public key encryption scheme. So the server does not have access to the explicit weights. So the idea behind homomorphic encryption is that you are performing the operation. So the aggregation that the cloud server performs with the model weight is done with the encrypted weights. The server does not see the weights at all. So this enables, for one hand, achieving an identical performance with variant trains without decryption. And the only thing that the trade-off is that this process more close to the federated linear framework, because there is this extra step of encryption and decryption that basically, for one, increases the size of the model. So you can see that the size goes from 2.8 megabytes to 62 megabytes, and also increases, of course, the transmission time from the hospital to the cloud server. And yeah, and there's a little bit of time in the processing of the decryption, the local step. Just to go over a little bit of the federated learning frameworks, just the base idea is that the server shares the model with each of the clients. The clients perform E number of epochs themselves in their local servers, and then they share their updated model weights with the server that aggregates all the way from the different clients to have a new version of the model. So it's a relatively simple idea. And homomorphic encryption basically adds just one thing to this federated learning framework, is the idea that basically the clients do not share the raw weights with the server, but instead they share an encrypted version of the weights. And because homomorphic encryption allows to perform operations on these encrypted weights, the cloud server doesn't need to actually have access to the raw weights, and they can perform operations and aggregate the information from the different clients, and then share back the weights with the client that they can decrypt to perform the operations, and the iteration goes on. So just coming back to the figure, this is with more context now what happens in this setting. So they also, moving on to the next part of the paper. So they also compare this model with radiologists. For this, they use 6 qualified radiologists with an average of 19 years of clinical experience. And for this, they provided the radiologists with the CT and labels from the train and validation split, and asked them to diagnose each CT from the test split into the 4 classes. And then they reported the performance of each of the radiologists, and the majority goes on this 4 classes problem, and also for COVID-19 versus non-COVID-19 problem. If there were multiple majority votes, they basically just went on and discuss until they reached consensus. So as I mentioned before, the UK data set also had a lot of chastity that had iodine contrast. So they also performed one more test looking at augmentation of the data with CycleGAN. So they basically use CycleGAN to generate non-contrast cities from contrast cities, and the opposite way also. So contrast cities from non-contrast cities, and they trade the 3D testnet on 4 different sets, so using only non-contrast cities, using non-contrast cities and CycleGAN synthesized non-contrast cities, using only contrast cities, and using contrast cities and CycleGAN synthesized contrast cities. This is just to show how an original CT with contrast looks like. So you can see the vessels have a lot of contrast there. And this is a cycle gun converted non-contrast CT. And this is what a non-contrast CT looks like. This figure just represents the framework of how they went about this. And just moving on to the results now. This is the result for the task of COVID-19 versus not COVID-19, which is the main task reported in the main paper, basically. So you can see with different colors, different lines of where the data was training, and these are the 3 different branches of the main hospital in China. This is the data from UK, and this is the federated model. And then this one is the test data from China, and this is the test data from the UK. So what it basically stands out is that the federated model outperformed the locally trained models in general. And it was kind of on par with radiologists. They could only do the comparison with radiologists in the China dataset, unfortunately. So that's the idea. And importantly, so training on the UK data performed very poorly, for example, when looking at the China data. So it's a very important concern, and it's very promising that the federated model actually was the better performance here. This is just the same, but in a table with the sensitivity and specificity here, and you can see the federated model outperformed the locally trained models in general. And this is the same results, but in this case for the test with 4 different outcomes. So you can see that for COVID, as we said, the federated model were better, and in every case, the federated model actually were better than the opposites, the locally trained models. But as you can see here, for example, detecting other viral pneumonia is a much more difficult task, not only for AI, but also for radiologists, as you can see in this figure. And this is the last bit of results from the paper, which is the trade-offs that exist between how many number of epochs is performed on each local client, so in each hospital, before transmitting back the information for the cloud server to update the entire model. So as they can show here, and it has been demonstrated with other types of projects also, the ideal in terms of accuracy is basically to perform 1 epoch per iteration. But of course, this encompasses more time because you waste a lot of more time during transmission. But in general, the performance of the model was not much worse if you train the model for more epochs in each one of the iterations. So they basically claim that the performance does not decrease a lot, and this saves a lot of time, basically. So a couple of takeaways from the paper is that the federated learning framework enables global training of CT-based AI model for precise and robust diagnosis. And this framework and the infrastructure that they created with this can be expanded, of course, beyond COVID-19 to other diseases that may be helpful. And that's it. Happy to take any questions.
Excellent. Thanks for the presentation, Julian.